Here's something that is going to be very new to my listeners. Stellar mass function. Astronomers and astrophysicists, when they look at stars, they determine their rate of evolution by how much mass is available. That's basically it. So they have what's called the stellar mass function, determined what the star's current mass is, or its initial mass when it's being measured. That is what is used to determine its eventual fate. And I wanted to juxtapose this to stellar metamorphosis, and it's very easy to do so. And hopefully I explain this with these little drawings I did here as precisely as possible, even though it looks kind of like haphazard. But the dogma has evolution of a star determined by its mass, its stellar mass function. Stellar metamorphosis is theory on developing evolution of a star is determined by its rate of mass loss. So it would be called a stellar mass loss function. The mass of the star is lost, and the rate at which the mass is lost determines what the final product is going to be, how large the final product is going to be. This is why we have moons of different sizes. This is why we have exoplanets of different sizes, evolving stars. So basically we have here the starting point, which is the initial mass for the objects that we observe. This is what establishment does. They have a starting point. So they have a large initial mass, and they start out like that. And the evolution of the star goes horizontal. So these would be the isochrons that the establishment has accepted as the star's evolutionary path. So say this is like a blue giant. It's only going to go along the blue giant's path. Nothing special is going to happen. It's just going to go along this path, and then they're going to tie together a whole bunch of other stars that maybe look similar to it to try to claim that that's the isochron, that's the evolutionary path for that specific stage in the star. So they go this direction. And they also have the initial masses of the stars, they vary. So for instance, the dogma says for stars, they can vary at different masses right when they're born. So let's just say this is an orange dwarf, or no, this is a yellow dwarf, this is the orange dwarf, this is a red dwarf. The red dwarf started at this mass, the orange dwarf started at this mass, the yellow dwarf started at this mass, and they all go like this. They all go completely horizontal on their own isochrons. Okay? So it basically what I mean is they determine what they consider to be the initial mass of the star, and then they determine what the star's evolutionary path is going to be. You see where the assumption is? They determined what the initial mass of the star was. They have no idea what the initial mass of the star is. They assumed that because they're looking at the star at its current state, that that's the state that it started off in, which is totally bogus. And we know this because, well, they just don't know what they're talking about. Let's just put it frank. Because right down here, they also have the stars starting off as their current sizes. The stars started off with the Jupiters, the Earths, the Marses, the Mercuries. They all started off with the mass that they have, which is totally insane. So everything just goes horizontal. They start. And that's how they can have stars like the sun, which would be like right here or right here, the same age as the most highly evolved stars, which they mislabel planets. That being said, the difference is I don't have the stars going off in that direction. I don't have isochrons where the whole thing evolves determined based off of a single mass function. I look at the star as having a rate of mass loss function because the star loses mass as it evolves. It doesn't keep its mass. It's radiating, it's hot, it has solar wind, it has flares, it has coronal mass ejections. These are objects that are clearly losing mass as they evolve. So to state that they have a single mass function and then you can determine the entire evolutionary history of the star based off of that mass when the mass is being lost, I think is, well, to be frank, it's delusional. It's not good science. And what I have here is the stellar mass loss function. So the stars when they evolve, actually all start off with a large initial mass. They all start off with large initial masses. It's not like the dogma where they have stars starting off at any size. It's not like that. You have stars starting off really big, really hot, and extremely energetic. And they go in this direction. They get smaller and less massive. So basically, the difference is the establishment, the dogma, has stars starting off, start. But what it actually is they start off with large initial masses and they evolve and lose mass. So the end result, the finish line, is much different than the starting line. But the starting line is always really big, really hot, and really bright. And the reason why there are smaller objects in the galaxy, planets that are different sizes, is that they have been losing mass at different rates. So of course this doesn't outline the fact that they lose mass at different rates. But it does point out that all stars, all of them have large initial masses. They all don't have smaller initial masses. You can't form a red dwarf in the state that it's in currently. You can't form a sun in its state that it's currently in. It needed to have evolved from a much larger, hotter structure, as well as Jupiter, as the Earth, as every single object in the galaxy. The objects that we see, that we observe, all started off with large initial masses, and they lose the mass as it evolves. So when you see papers, or when you read the dogma's papers where it has stellar mass function, keep in mind that's where they go seriously wrong. They state that there is no how do I word this? Gosh, I forgot what I was about to say. But anyways, that's the main difference. You see, these are isochrons, and then they separate the oldest stars, they call them planets. But really what's happened is there is no isochron data. What you see is what you get. If you have a orange dwarf or a yellow dwarf or a red dwarf, those were up here at one point in time. They were really freaking huge, and they're really hot. And as well, this theory also covers the fact as to why, outside of the stellar mass function, as to why it takes stars a longer period of time per stage of its evolution to evolve. For instance, the stellar mass function, of course, they have it right to where a blue giant has a very short life, and then the smaller objects, such as the red dwarf, its life extends considerably. They had that right, but for the wrong reasons. The reason why the star loses mass, or the reason why the red dwarf has a much longer extended lifetime, is because it's losing mass slower per unit volume, per unit mass. It's losing mass slower. And as it cools and evolves from earlier stages, it takes that much longer for that mass to be lost. And then it is subject to radiative ablation from hotter hosts, and it's subject to atmospheric escape from the lighter hydrogen constantly escaping from the surface. It's subject to a whole lot of other variables other than its own internal energy production. So keep that in mind when you look at the stellar mass function. They don't have mass being lost when the stars evolve. The dogma doesn't like mass loss. It's very inconvenient for them for stars to lose mass, because it means they have to replace all their functions and they have to rewrite everything. It's a lot of work to rewrite that kind of stuff, and I just want people to know that's the main difference. So to recap, you have stellar mass function, where a star is determined by its mass alone, and then you have stellar metamorphosis, which determines, okay, the star's mass is lost as it evolves. So its rate of evolution is determined by how fast it's losing its mass. All right, you guys, I know today is October 17th, 2019. Later.